So the first thing that we're going to look at in this quick tutorial about polarity is that we're talking about the polarity of a molecule, not whether the bonds within them are polar or not per se. We use electronegativity difference to decide if something's got a polar bond inside it. The best thing to do when you're doing a question based on whether a molecule is polar or not is to assume that all bonds are polar. Now, it's not always going to be true, but you can justify polarity better if you just make that assumption first up, and then in your long answer, say that you made that assumption. I assume the sulfur-oxygen bond is polar, or I assume the carbon-chlorine bond is polar. Okay? Then if you go on to say which one you think is delta plus and which one is delta minus, that will also help you justify your answer. Okay? Of course, carbon-carbon, hydrogen-hydrogen, nitrogen-nitrogen, anything where the atom is the same, you know that the electronegativity difference has to be 0, so you know that's non-polar. Another one that's worth keeping in mind is that you should know, this is an exception to our E rule, you should also know that the carbon-hydrogen bond has a difference of 0.4 for electronegativity, so we class this as non-polar as well. Okay, that can be very, very helpful. So, unless it's carbon-hydrogen or an atom with itself, then we should assume that it's polar. And in that, you should in your answer state which one you think is delta plus and delta minus, because that will help with your answer. In molecular polarity, as well as knowing about bond polarity, you also have to look at shape. Because shape is going to have some determination on whether those polar bonds cancel out or not. So, remember your shapes. And they will come from Lewis dot diagrams, whether you've drawn them yourself or whether the examiner has given it to you. And ultimately what we're looking for is electron distribution around the central atom. That's what you really is determining polarity. So it's electron distribution okay, so if we keep those three things in mind, we can sort of create a checklist or a flow chart in our mind of how to work out if something's polar or not. We're going to start with looking at ammonia, Nh3. The first thing that I would suggest you do is actually draw a simple Lewis dot diagram for it, because that will help you work out whether there's lone pairs on it and stuff like that. Because lone pairs are a bit of a giveaway that it'll be uneven or asymmetrical distribution of electrons, because lone pairs have more of a repulsive force than a chemical bond does. So when I do my Lewis dot diagram, I see that we've got lone pairs on the nitrogen. Okay, so automatically I can make the assumption that this is a polar molecule, because the lone pairs are going to repel these three bonds, and that leads me to my next step, is I'm going to draw a three-dimensional diagram for this. Here I've got 1, 2, 3, 4. I've got 4 regions of electron density, 3 chemical bonds, 1 lone pair of electrons. So that means around the nitrogen I've got to have my shape for 4 regions of electron density. Here I've got lone pairs on top, so I'll put them there. I'm not going to put an atom at the end of that. Put a hydrogen here, here, and here. My next thing is to remember my shapes. 4 regions means it's a tetrahedral electron cloud, but with only 3 atoms bound, it's going to be a trigonal pyramid. So now I'm going to write in my shape. Trigonal pyramid or trigonal pyramidal. Here is where I'm going to say, okay, well, what I'm going to have here is an asymmetric shape, because that is one of the asymmetric shapes. So bent or V-shaped is asymmetrical. Trigonal pyramidal is asymmetrical. What's another one I can quickly think of? Probably for the numbers of electron density, that's about it for you guys. So that's easy. So this creates asymmetrical electron distribution around the nitrogen, which is what we class as the central atom. We know it's the central atom because of how we've done our Lewis diagram. And in our explanation, we would then say it's polar. But which end is going to be delta minus and which end is going to be delta plus? So where is the dipole? If we're going to assume that all of these bonds are polar, and by the way they are, which way would the arrow go to show our dipole in the bond? Would it go towards the nitrogen or away from the nitrogen? Towards it. Why? You're quite right. It's not actually with the electrons, believe it or not. That's just repelling those to create the shape. To create the dipole, it's more to do with the fact that if you look at where nitrogen is in the periodic table, it's up the top right-hand corner, or very close to it. They are the very electronegative elements. So the dipole in that bond is going to be in this direction. Yes, the electrons have an effect as well, but this is our key thing for drawing in our dipoles. And if you want to be fancy about it, you could turn those into vectors, so make sure the length of those are all the same size, because it's the same element being bound to it. So that would therefore create a delta plus at the bottom, and conversely, of course, delta minus on the top. Okay, so my thought process went through quite simply. It's got lone pairs of electrons, so I know it's going to be polar. But now I need to explain why it's polar. And I explain it by looking at its shape, its dipoles, and now I can label its delta minus and its delta plus. I can label the dipole. So I've now got my explanation. I also need to talk about the fact that with this shape, we've got an asymmetrical electron distribution around the central atom. Okay, any questions on that one? Water is easy to explain the same way. It's a bent shape, two lone pairs of electrons, two hydrogen oxygen bonds, and they're common ones in exams. Okay, EG number 2, a little bit harder. CCl4. So what's my first step that I should do with this? Sorry? No, just before the shape. Lewis dot diagram. So I'll do my Lewis dot diagram first. Now you'll sometimes be given that. So this step one's sometimes done for you in exams. Now, here you'll notice there's lots of lone pairs of electrons, but they're not around the central atom. So they're irrelevant. They're completely irrelevant. There's no lone pairs around the central atom, so your immediate inference would be this is non-polar. Immediately you think that, but you've still got to confirm that. So I draw my three-dimensional diagram. So that's my second step, so well done. We got, so how many regions of electron density around central atom? 4. So I draw the same shape as I did for ammonia. You'll notice I don't bother with the lone pairs for a shape. I can drop them out now. I'd only put them if it was around the central atom that I had lone pairs. Then what's my assumption about all the bonds in here? Because they're carbon with a different atom. That they're polar. I look at where chlorine is on the periodic table. Whereabouts is it? Top right. So the arrows are going to go towards or away from the carbon? Away from the carbon towards the chlorine. Sorry, I was being clever there, phrasing it, talking about the central atom. So we've got delta minus, delta minus, delta minus, delta minus. Well, hang on, if they're all delta minuses, and this is a symmetrical shape, tetrahedron, so four-sided, three-dimensional shape that is equals, that's the hedron bit, then what's going to happen with these dipoles?
They cancel out.
They cancel out, okay? So here you have a net dipole, overall dipole of 0. Think of them like little tug of wars, a four-way, three-dimensional tug of war. There's going to be no movement on that tug of war because these arrows are all meant to be the same size, same atom, okay, same atom. They're all meant to be the same size, and they're pulling at the four corners of a tetrahedron, which is a symmetrical shape. So they cancel out. So you have symmetrical electron distribution around the central atom. So even though you have polar bonds within the molecule, you have a non-polar molecule. Okay, example number 3, which will be our last one. That's not the right way to write that. Let's put the hydrogen first. Okay, dichloromethane, this is called. It's a pretty similar chemical to this one. It's got 4 covalent bonds. It's got a tetrahedral shape. So, let's race through the process again. Again, the fact that these don't have any lone pairs and these do, irrelevant. It's about the central atom. Okay? So, 4 regions of electron density, what shape?
Tetrahedral.
Tetrahedral, good. Okay, now, here's where our little exception to the rule becomes important. Remember, CH bonds are they polar or non-polar? Non-polar. Okay, for this year anyway. CCl bonds, though, are polar. So we're going to have an arrow there and an arrow there. Well, if that was a tug of war, these two would be pulling the carbon in this direction, wouldn't they? Because there's not enough force here. Actually, those ones are slight arrows that way. Very, very small arrows towards the carbon. So here we create a dipole. This side of the molecule, this pole of the molecule is delta minus because that's the way the arrows are going. So therefore the other side of the molecule is delta plus. And so the trick for you to get excellence is to be able to explain that in terms of electron distribution, shape, and the polarity of the bonds within. So you'd say here that the carbon-hydrogen bond is deemed to be non-polar because the electronegativity difference is less than what? Bit more, bit less than 0.5, less than 0.5. Okay, so less than 0.5. You'd say that the CCl bond is polar because the electronegativity difference is 0.5 or more. The 1.6 that some of you said, that's going to ionic. That goes all the way to ionic, so that wouldn't be a molecule. Okay. Any questions on that before I stop this? All right.